Hello everyone, my name is Naz Iqmal and I'll be introducing you to one of the most important topics in air pollution and control, which is atmospheric dispersion modeling. Listed here are the contents for this topic. We'll be going through the introduction, followed by the physical explanation for the dispersion, then the Gaussian model, tall stacks and plume rise, critical wind speed, other stack design considerations, computer program for design modeling, and lastly, it will be the mobile sources and line source models. Now for the introduction. With the onset of the Industrial Revolution, to prevent the indiscriminate abuse of the atmosphere, it is necessary for people to recognize the need for more and better pollution control equipment. History has demonstrated that harmful effects occur when pollutants build up to high concentrations in a local area. The accumulation of pollutants in any localized region is a function of emission rates, dispersion rates, and generation of destruction rates, that is by chemical reaction. Modeling is essential, and there are several reasons why modeling must be conducted. The first is that it is impossible to measure the impact from a facility that will be built in the future, but we need to have a reasonable estimate of that impact before we allow the facility to be constructed. Next, a comprehensive measurement programs could be 1,000 times more expensive than modeling and would also be subject to errors. Then, modeling is the only practical approach when there are many sources and when we wish to isolate the potential effects of just one source. Lastly, modeling provides an impartial and reproducible tool for assessing and comparing the various alternatives. Shown here are the figures representing the ideal physical dispersion model for any pollutants and gas, where we have figure 20.1, which is the spreading of a band-over plume. Figure 20.2 describes the top view of an instantaneous plume and a 1-hour average plume and the corresponding concentration profiles. And lastly, we have figure 20.3, which is the behavior of the downwind elevated transverse concentration profile as a function of distance downward. Now all these figures that you see on the slide are models which show a continuous stream of either gas or pollutants into a steady wind in the open atmosphere. For most models, the pollutants will rise, then bend over, and travel with the mean wind, which will dilute the pollutants and carry them away from the source. Now let's ask ourselves a very important question. How does dispersion take place? Based on figure 20.1, it depicts the physical stack height, h, the plume rise, m, and the effective stack height, capital H. It is intuitively obvious that matter behaves properly by moving from a region of high concentrations to one of lower concentrations. Eddies may intercept part of a narrow plume and quickly interchange a batch of concentrated pollutants with a batch of clean air some distance away from the plume. The combined effect of many eddies of various sizes is to broaden and dilute the plume. Mechanical eddies result from the shear forces produced when air blows across a rough surface. Surfaces with greater roughness, such as trees or buildings, create more eddies than smooth surfaces. Examples are ice and snow. Similarly, a stronger wind produces more eddies. Now for figure 20.2, it describes that in a time average pollutant concentrations at a given distance, x0, downwind from the source is normally distributed in the y direction. However, the instantaneous concentration profile in the y direction at x0 is vastly different. Now figure 20.3 is the productive version of the latter, where it points out that as the distance x0 increases, the pollutant spreads further in the y and z direction, and maximum concentration will eventually decreases. Next, let us touch on the most favored mathematical model that is frequently used for any air dispersion modeling, which is the Gaussian model. On the top left, we have equation 20.1, which is the general equation describing the Gaussian model, where we have C as the steady-state concentration at point x, y, z, Q the emission rate, sigma y and sigma z as the horizontal and vertical parameters, And these are functions of distance, x, and atmospheric stability. And then we have u, the average wind speed at stack height, y, the horizontal distance from plume center line, z, vertical distance from ground level. And lastly, h, the effective stack height. And h is apparently equals to h plus delta h, where h is equals to, as in small letter h, is equals to physical stack height, and delta h is the plume rise. On the right, we have figure 20.4, which describes the coordinate system showing Gaussian distribution in the horizontal and vertical. Now, without the second exponential term in equation 20.1, equation 20.1 can actually be split into equation 20.2a and 20.2b, where the only difference is the exponential term at the back here. Figure 20.5 is a schematic diagram depicting A, a mathematical dispersion of pollutants underground, and B, a reflection due to an image source. Now, based on figure 20.5a, it is a pollutant dispersing infinitely in the z direction, including underground, and this is impossible. And because of that, the model is then corrected to that of figure 20.5b, where it is added a fictitious image source underground emitting at negative h, which adds to the above ground concentration an amount exactly equal to that lost underground by the real source. On the right, we have figure 20.6, which is a variation of ground level centerline concentrations with distance downward wind from an elevated source. It is a bell-shaped graph. The atmospheric stability classes is a crucial element of the Gaussian model. Now, air is termed unstable when there is good vertical mixing. This occurs with strong insolation combined with light wind. As a result of absorbing solar energy, the Earth's surface heats and then warms the layers of air near the ground. The warm air rises, promoting vertical mixing. Stable air results when the surface of the Earth is cooler than the air above it. Then the layers of air next to the Earth are cooled and no vertical mixing can occur. Because the dispersion parameters sigma y and sigma z are strong functions of atmospheric stability, as well as downwind distance, it is important to discuss the estimation of these parameters. Figure 20.7 and 20.8 were developed by applications of theoretical principles to the analysis of actual dispersion data. Tests were conducted in level, open terrain, in which short time average in about 10 minutes concentrations were measured, along with emission rates and wind speed. Extrapolation of the data were made to extend the graphs for values of x greater than that of 1000 meter. Because of the restrictive circumstances under which these curves were developed, predictions of concentrations using the Gaussian model should be expected to be closer to about plus minus 50% of actual values. Now on the top right, we have table 20.1, which is the stability classification. And below it, we have table 20.2, which is the values of curve fit constants for calculating dispersion coefficients as a function of downwind distance and atmospheric stability. Moving on, let's have a look at the dependence of concentration on averaging time. Here we have equation 20.5, where T is the averaging time in minutes, and Ct is the concentration of averaging time in terms of T. Now the averaging time, if it is less than 10 minutes, the exponent is more likely in the order of 0.2 instead of 0.5. And a longer time average concentration will be expected to be lower than a short time average, owing to wind shifts and turbulent diffusion. The maximum downwind ground level concentration always occurs on the center line. Turner in the year 1970 developed a graphical means of estimating the maximum concentration, Cmax, and the distance at which it occurs. Both Cmax and Xmax depends on the stability class, effective stack height, wind speed, and emission rate. Figure 20.9, which is the maximum Cu over Q and distance to Cmax as a function of stability solid lines on effective stack height, represent Turner's results as a plot of Xmax versus Cu over Qmax. The solid lines represent the various stability classes, and the numbers along the lines represent various values of the effective stack height. Figure 20.10 is the behavior of ground level centerline concentration from an elevated source as a function of downwind distance at A, atmospheric stability at constant H, and B, effective stack height at constant stability. Now notice that as stability changes from unstable to stable, Cmax decreases slightly with Xmax, while Xmax increases. Also, the region of relative high concentration is much larger than stable conditions. Now the plots in figure 20.9, if they were to fit a polynomial equation by Wen Chu in 1979, it can be written as equation 20.6. An elevated inversion can act as a lid to prevent the upward dispersion of pollutants as shown in figure 20.11 here. An assumption is usually made that the inversion layer reflects pollutants similar to the way the ground does. And the equation that models a trap plume is described by this equation, equation 20.7, where L is equals to the height from the ground to the bottom of the inversion layer. In practice, it is only necessary to vary the summation index J from -2 to +2 to obtain reasonable convergence. During the breakup of a ground-based inversion, fumigation of a plume can occur. And under these conditions, the equation that best describes the downwind concentration is equation 20.8. Turner, in 1970, suggests that equation 20.8 is also valid for the plume trap under an elevated inversion at height L if L is substituted for H and if X is sufficiently far away from the source. The sufficient distance is set equal to twice the distance at which the edge of the plume begins to interact with the inversion layer. If the distance of the interaction is XL, then according to Turner, sigma z at this distance is given by equation 20.9. Now, there are also instances where the Gaussian equation is not valid. Two examples are the case of dispersion within a long traffic tunnel through a mountain or dispersion in a narrow valley capped by an inversion. In those cases, a simple box model approach is often sufficient, following equation 20.10.